warm welcome here in our QWare area 42. This area is specially designed for our employees and for the Munich IT community to meet each other, to collaborate, and also to play and party hard. I think all of those parts will be addressed today. It's a great honor to be the venue sponsor for the Munich Datageeks, and it's the largest event here since we opened the gates a few months ago. Today my name is Josef. And I'm a co-founder and CTO of QWare. Representing QWare today. Today I want to talk about time series processing with Apache Spark, a solution we developed which is called Chronic Spark, where we are able to process large amounts of time series data. But first, I have a few words concerning QWare. As I know you're Datageeks, I've collected some KPIs. You also find them on our website. We're a custom software development company located here in Munich and also in Mainz with a little bit more than 80 employees, and we're focused on doing fixed price projects. And we're very glad that we received the Great Place to Work award this year, the first place. So our employees are doing well here. These are our customers. We're doing most of our turnover with the large ones like BMW, Deutsche Telekom, Allianz, but also have some small projects for FC Bayern or so. And our main portfolio is being software paramedics and to heal ill systems, if they're not performing well, if they have problems with maintainability or so, we try to heal them. And we are also an inventors workshop for our customers when they need solutions for especially cloud native computing based on frameworks like ECOS, Kubernetes or OpenShift. And we're also doing a lot of big data projects, mostly on Apache Spark. That's why I'm talking about time series processing with Apache Spark. And one focus topic here is also the Internet of Things. We're helping Deutsche Telekom to improve their connected home platform called KiwiCon. It's the largest connected home platform in Europe based on Eclipse Smart Home, and we're helping them to improve. That's all to QWare. I want to hold it short. So now let's enter time series processing. So first, a few basic terms concerning time series. We're surrounded by time series. A lot of data is best represented as time series, like operational data from monitoring systems, performance metrics, or even log events. Also, data warehouse systems have their dominant dimension time, and so they can also be interpreted as time series. Those Internet of Things stuff like measured me or sensor data, financial data, climate data as shown here on the right, and we also did time series analysis with web tracking tools like clickstreams. They're also time series. So what do we have to know? What are the basic terms if we handle time series? One term is univariate time series. It's a time series where we have one value at a certain point of time, and multivariate time series where we have multiple values at a certain point of time. Very important one, we'll see this later on, are multidimensional time series, where we assign a time series into a multidimensional space, where we measured it, what's the unit, where geographically we measured it, on which object we measured it, or which series logically is it. These are different types of time series, and there's also the term observation we'll use later on. Observation is the value at a certain point of time. It's called an observation. And time series sets are obviously sets of time series which are belonging somehow together. These are the basic terms. So if you have your time series, you can think of different kinds of operations to perform on those time series. There are basically two types here, operations which are projecting time series on time series and time series on scalar values. A few examples here. For the first kind, an align operation where you align two time series at a certain point of time. You align them. You can think of diffing time series. You get the diff as a time series. You can downsample time series. You sample them at a certain interval. You have them downsampled afterwards. Or a little bit more complex, you can detect outliers. If you have monitoring data, it would be important to know if there are any outliers, that there is a possibility that there is an anomaly there. Other type of operations, where the output is a scalar value. A very trivial one is min-max. Find the min-max value of a time series, or average median. The slope is sometimes also interesting, and or the standard deviation. You can calculate the deviation of the values within a time series. So what's our use cases after having cleared those basic terms and a few examples what operations on time series can be? Our use case was analyzing the operational data of a worldwide distributed business-critical application. And we wanted to perform root cause analysis when the application acts in strange ways and anomaly detection. This system has more than 1,000 nodes distributed worldwide, about 10 processes per node running. We're collecting more than 20 metrics per process, on the operational system level, on the JVM level or so. And we measure it each and every second. So if you calculate this leads to about 6.3 trillion observations per year. And we wanted, or we do, data retention of 5 years, so we can analyze 5 years of data within this application monitoring data. Yeah, and this is a huge amount of data, trillions. This is really, really big data. So we have to look for a big data solution here. And one very important part of big data solution is you have to scale like a boss. You have to scale horizontally as much as you can. And the solutions we evaluated, which are available on the market, especially as open source projects, didn't scale enough for our use case. So we built an own stack and open sourced it. It's called Chronix. You can find it at this website, the Chronix.io website. And this is the overall architecture, big picture of Chronix. You have 3 building blocks. The data ingestion or collection building block, the core block, which stores the data and processes the data, and the visualization building block where you can analyze the data. So at the collection building block, we're able to ingest data from Logstash, FluentD, CollectMe, and a known collector, which collects some metrics via JMX or SSH. And we're also a long-term storage for Prometheus, cloud-native monitoring solution. Yeah, they're collecting the data for us. The data is then stored in this stack. In common, all those parts here, they have a common format. It's called the Chronix format. I'll focus on this later on. This is how we encode and decode time series data. And the stack is, we use Lucene for the chronic storage in one node. We use Solar Cloud for distributed data storage, and we're using Apache Spark for the number crunching to analyze this data. And you can access this stack from Zeppelin. We have a Zeppelin connector which is able to connect to Chronic Spark. And we can write operations going to Apache Spark in Zeppelin. We can also do SQL statements and SQL queries on time series data within Zeppelin. We have an own user interface, a rich client user interface called Chronic Analytics. I have some screenshots this later on. And we also have a connection, a plugin for Grafana. You can chart those time series within Grafana. This is our Chronic stack. It's, we started developing the stack 2011. Starting point was a project at BMW, but then we launched a research project with the University of Erlangen-Nuremberg, and for 3 years or so, and we assembled the Chronic stack stepwise. Yeah, today I want to focus on Chronic Spark, how we leverage Spark to do time series processing here. And the basic architecture of Chronic Spark is, as I told you, we use Solar for distributed data and also for some basic data retrieval. Solar is very good in slicing and dicing in a multi-dimensional space because you have those attributes and you can query this very good. Solar can also perform low-level aggregations. But on top of Solar, on top of the Solar Cloud, we're using Spark for the distributed processing tasks. We want to perform higher level operations like outlier detection or anomaly detection. This is better implemented within Spark. And Spark gets its data from the Solar shards. Each partition here is equivalent to one shard at the Solar side. Yeah, and you have different options how you can do the result processing afterwards. As you might know, you can use Java or Scala to do this, but there are also connectors for Python or R. You can formulate your distributed processing tasks. Yeah, this is the overall architecture of Chronic Spark. Here's some screenshots how we're using it. One example is our Chronic Analytics workbench. It's not yet open source. We're working on it right now. It will be open source within the next month. And here's one screenshot. You have we're having a multi-dimensional time series within our Chronic stack. So you have here the possibility to drill down into those dimensions. You have also the possibility to query certain kinds of time series and the time frame you want to get analyzed. And here multiple time series are visualized. And this is a basic trend visualization, but we have also some more complicated visualizations like the box plot here. Within Chronic Analytics, we're also performing anomaly detection based on Twitter anomaly detection on this open source project here, and Yahoo EGAT. We're using both to highlight regions of a time series which are probably an anomaly. So we can act in some ways. We can try to reboot the system, observe it. Yeah, that's the use case here. So let's get a little bit deeper into what Chronic Spark is, how you can use Chronic Spark. But first of all, this is our goal. It should be an easy to use big time series, data storage and processing on Spark. It should be really easy to use. We're not only focusing on data scientists, we're also focusing on software engineers like myself. I'm not a data scientist, sorry for that. I'm a software engineer, and I also want to perform my queries on time series there, so it should be easy to use. And also Jeff Norris approved, of course. So the first question is, what time series model do we stitch into? And the time series model we're using within Chronic Spark is that time series are a set of univariate, multidimensional, numeric time series. A set of time series because we're more flexible. Yeah, we can address a set of time series. We can ask questions like, give me all time series for a project X everywhere globally. So I have a lot of time series in this set, and I can detect anomalies on all of those. Yeah. This feels more flexible. And also, if you have a set of time series, it's easier, or you can better parallelize the operations. And a time series is a basic unit of parallelization at Chronic Spark. So it's good to have large sets of time series here. It's univariate because multivariate time series will introduce a little bit too much. My notebook tries to tell me something, you know. Because multivariate are a little bit too complex, and we have our sets of time series. So in our use case, we didn't need to have a multivariate time series. So they are single time series, they're univariate. They're multidimensional because it was important to have the ability to slice and dice and to search, to drill down into different kinds of time series, as you have seen on the screenshot before. So we decided to have multidimensional time series here. For monitoring, this is very important. Yeah? We have our time series, and it's assigned to a process dimension, it's assigned to a node dimension, it's assigned to a geographically distributed dimension. This was important for us. And numeric because it's the most common use case with monitoring data. Actually, we're just right now working on providing a little bit more than numeric time series here because we also want to analyze log events. Maybe more than numeric in the near future. Yeah, this is our Chronic Spark time series model. The interface to Chronic Spark is quite easy. You have two classes, which are the whole interface. You need to know how to interact with Chronic Spark. You have the Chronics RDD. RDDs are basic abstraction within Spark for distributed processing. And then a Chronics RDD represents a set of time series. This is our abstraction here. This is our time series model. It's a set of time series within a Chronics RDD, and it provides some distributed operations on this set of time series. And with the Chronic Spark context, second class, and its concern is to create Chronics RDDs and to interact with the Chronics server, the Solar Cloud, in the backend, once to the backend. Those are our two interface classes here. Here is the interface of Chronics RDD. It extends Java RDD and is a RDD of metric time series. Yeah? This is numeric time series, and the RDD is a set of time series. You have a few operations on this set of time series, and you also have here at the bottom transformation operations to transform this RDD into a data frame or a data set. Spark provides three abstractions for distributed processing. One is RDD, second is data frame, third is data set. We want to provide them all because they have different properties. RDD was the first abstraction available within Spark. It's typed. Yeah? As you can see here, this is a typed metric time series. It's optimized in some ways. It's major, and but you can perform no SQL statements on an RDD. That's why Spark introduced data frames a few years ago. They're not typed, they're tables. The abstraction is a table. They're highly optimized, also on the road for some years, and you can perform SQL statements on those data frames. So by transforming our RDD into a data frame, we're then able to perform SQL statements on time series data. And very young abstraction is the data set. Gets stabilized within Spark 2.0. It's typed. It's highly optimized in contrast to the RDDs that are optimized. The data set is not so mature, and you can perform no SQL statements there. Yeah? So each of those abstraction has its own properties, and we decided to provide them all. Now let's have a look on this metric time series data type. As you can see here, the Chronix RDD is typed against metric time series. This is our time series abstraction, and this is a set of time series. And the metric time series data type provides also some operations you can use. There is one operation where you can access all timestamps of a time series. Also, obviously, one to access all numeric values. The others here. And for a little bit more convenient access, there is also a method where you can stream the observations out of the time series. And you get your pairs of timestamp and value within a stream. And here is one method which is representing the multidimensionality of the time series. With these attributes you get out a metric vector, and this is where you can find your dimensions or define new dimensions for this time series. So, a little bit code. When you actually want to, if you decide to use Chronix Spark this evening, you grab a beer, get into this room and hack a little bit. The first thing you have to do is to set up your development environment and to use the Chronix Spark context. And there is one method, very important, called query. And with this method you can get your Chronix RDD. What do you need? You need to provide a Solr query. This is a query for grabbing all those time series relevant for your set. You have to, this is a technical thing, you have to tell him where a zookeeper host is to find all Solr cloud servers. This is a database name, and this is an adapter to serialize data from Solr into Spark. This is the code, sample code. After this sample, you're able to perform operations like, in this case, min-max or mean. You have to initialize a Chronix Spark context, basically providing a Java Spark context. Then you have to define your Solr query. Here, we use a query against the metric dimension, where we query all metrics available or all time series available for heap memory usage used. You get no matter which process, no matter which node, you get all those time series back with this query. And then you have to perform your query here. Provide the Solr query. This is the zookeeper host. This is the collection name, and this is all cloud storage. And then you're able to perform your queries or your operations. Quite easy, I think. If you don't want to code like this, you can also use a notebook like Zeppelin, as I told you, to query those time series data. Here's one example. Yeah. These are normal SQL statements here. You select the timestamp, the value, the process, and metric. Those are dimensions from the time series table, where metric is memory free or metric is CPU used, user space, sorry, and order by timestamp, of course. So you can, afterwards, you have your charts here. Yes, this is a deadline, the CPU user space, the memory is a chart. Yeah, so you can use it also in a little bit more convenient way. So a few, let's open the black box a little bit, and I'd like to present you a few of the internals of Chronic Spark. One very important internal is our storage format. How we store time series within Solar documents. And the basic idea, it's not a revolution, it's quite easy. If you have your time series here, we're doing chunking. Yeah? We chunk one time series, one is potentially very large, with a large time span. We chunk it into regions. And the chunks are not for a specific time span. The chunks are for a specific amount of values. And we count the amount of values. 1,000 values or observations within one chunk. Yeah? So they can span different time spans, one chunk. So it's just chunked, this time series, and one of those chunks is stored in one physical Solar document, and which attributes do we provide there? A start timestamp, an end timestamp of this chunk, a unit, the dimensions, and the values. It's a little bit more than values. It should better be named here as observations. Yeah. Here it's byte encoded, the values and the timestamp. Yeah. So basically here is byte encoded observations. Those observations are byte encoded with with Google RPC format protocol buffers, and the timestamps are delta encoded. What's the idea here? If you have your start time point and end time point, you know how many values you have. So you can think of a homogeneous distributed timestamps. Huh? And this is not the case normally with monitoring data, because they're not very homogeneously distributed. There are few diffs in between, so we only store the diffs to a homogeneously distributed timestamps. And we also do delta encoding on the values. Yeah? If the value is every time the same, we don't store any value, we just store 0. That's why we're space efficient here. We did some research on how big a chunk should be in terms of number of observations, and what's a good compression codec for our bytes here. And we could figure out that gzip with 128 kilobytes within a chunk is the best fitting configuration of our compression codec and chunk size. Yeah, we're not alone. This is our big data landscape, and there's also a region here which time series are available. It's not only Chronix, it's also InfluxDB, you might know, or OpenTSDB. Prometheus is also some kind of a time series, and a few more. So we did a comparison. First, we did a benchmark on storage demand. Yeah, if you have, this is the amount in gigabytes here. The raw data in two projects was 108.2 gigabytes, and we ingested it into InfluxDB, OpenTSDB, KairosDB, and Chronix. And as you can see here, Chronix performs best out of 108.2 gigabytes raw data. It's resulting in 8.7 gigabytes data within Chronix on disk. Place 2 is InfluxDB with a little bit more than 10 gigabytes, and so on. So through our data, most importantly the data encoding of timestamps and values and the compression codec, we were able to be the best in storage demand. And we also did a benchmark on performance. We have we've measured different kinds of operations, from very basic operations like average, max, minimum, to high-level operations like outlier detection, trend detection, frequency detection, and so on. These are especially very useful in doing anomaly detection. And as you can see here, we're performing not so good in this basic operations, but if you have your high-level operations, Chronix performs also best in some, because we've implemented all those high-level operations within Spark, and also doing predicate pushdown onto Solar.
Why did you test it on one node?
Yeah, well, it's only on one node, only because it was the first step. We're right now on this measuring it on a whole cluster, but this was our first step. So, yeah, that's a disclaimer. Yeah.
Sorry, the units are seconds? Or?
Seconds, yeah, sorry.
And the left is the weight?
No, sorry. Should look. This is can't be seconds.
It's time.
It's time.
And on the left, do you weigh the different benchmarks, or
no? Just sum it up.
Okay.
Just sum it. Yeah, so. Great data science mistake I did. No units. There you can see I'm a software engineer. Yeah.
You're using container technologies for the scale-out stuff as well, like Postgres or?
We're using, to scale out, we're using the possibilities within Solar, so Solar Cloud. It's not based on containers. And for scale out on the data processing plane, we're using Spark. And it's also not on container technologies. We have one showcase on top of DCOS, and we're using Spark on DCOS, and this is a container solution. Yeah.
So you're planning benchmarks with that as well?
With container solutions?
Yeah, with the data center.
Actually, the benchmark right now we're doing for distributed Chronix, it's based on this DCOS setting.
Oh, okay.
Yeah.
One question. So you said the focus in your talk on the operations from time series or from time series to scale.
Yeah.
So I would be very interested in the identification and evaluation of substructures of time series. So let's say finds the position of all relevant peaks in the signal and determines their width and height, for instance. So do you plan to support something like this also out of the box?
And this can't be represented as time series? Don't you think it, if you have, because a subset of a time series only containing the peaks can also be represented as a time series, only containing the peaks.
Yeah,
Or
so
do you need more information?
yeah, I also want to process especially this information. So after I found all the set of peaks, so which is a discrete set of course,
Yeah.
of the positions, and then to evaluate also the width and the height of them, and to take just this triple of numbers
Okay.
and make a table out of it.
So your result will be a set of
Yes,
numeric
exactly.
values. We don't provide this possibility right now, but you can easily enhance the Chronix RDD to do so.
Okay.
So the Chronix RDD is open for your own operations, and you can enhance it.
Okay, and for this identification step of this structure, is there any kind of support for this?
To identify peaks,
Yes. So of a certain width and height, for instance.
we only can identify peaks right now, but of a certain width. You mean the interval in between peaks, or how high it is in absolute
No,
number?
the width of the peak itself. So not a single point, but also some kind of cusp, for instance.
Okay, no, not right now. It's not within our basic operations. But
I see.
as you can access all observations within a Chronix RDD, you can implement this by yourself.
I see. Thank you.
Okay, nearing the end. Yeah, here are the contributors. Much thanks to my contributors on Chronix Spark. Also, the cloud is a great contributor. And this is the guy, the mastermind behind it. He did the photo behind Chronix. He's our PhD student. He takes pictures and also programs Chronix. That's how things go. Yeah, now I'm at the end. I hope time is right. Yeah.
Thank you.
Thanks.